Thanks for having me. Happy to be here, especially among friends. Some of you I know for 3 decades, and I'll talk about some of the recent work I've been doing in the last 3 years that relates to game theory. So this is Llama doing game theory, this is Llama in Slovakia, and this is Llama in Bratislava. However, I could not use Llama to generate those images in Europe because it's forbidden due to European regulations. So I use actually Gemini and GPT-4 here. All right, so I'm going to talk about particularly about algorithms that I use to fine-tune these models, and I've been lucky that I've been involved both in fine-tuning large language models and at DeepMind and in Meta. In DeepMind it was Sparrow, Google for Code, Palm and Gemini, and in Llama it was in Meta it was Llama 3. So right now, if you go to either Gemini, Google.com or AIMeta.com, the algorithms that you'll be interacting with will be the ones that I fine-tune at the very end with the algorithms that I'm going to present now. Oh, I haven't said it, but please interrupt me anytime with the questions. I didn't prepare any question time, so anytime just yell at me. I don't need to go over any slides. So there's a lot of work and a lot of people that went to in the creation of the things that I'm presenting. These are some of my students, interns, postdocs, collaborators, people in DeepMind, people in Meta, people that I brought from DeepMind to Meta, and people from other universities work with, in particular people from Princeton and Berkeley. So this is based on some of the work that we presented recently 3 months ago in the ICML here in Vienna and iClear, and some of the work that will be also presented because it's submitted for the next year. All right, so what is the plan today? I'll talk about the algorithmic alignment of large language models. I'll describe, why the stuff that has been done and at the beginning with ChatGPT is not something that I think is good, and I'll try to convince you how to do it better and how we convince leadership in DeepMind and Meta to go this way, and what particular algorithms we apply for that. So in general, we would like to create, some AI algorithms, that would take as limited amount of human, work to work as possible, right? So we would like to have some systems that will be helpful for us, but we should not spend a lot of time labeling them before they become useful, right? So something that's called either unsupervised or semi-supervised or self-supervised or algorithms with little supervision. And so large language models are part of those that were enabled to train big algorithms with many parameters. That's right now, the things that are public are about like 500 billion parameters. Right, so this is kind of the traditional recipe that may not need to be always preserved, but this is something that like last year was like a basic cookbook of what we do. Mostly based on this self-supervised learning. So at the beginning we have a pre-training phase. So we take all internet and we train, big network to predict the next word. So something that just continues talking, some kind of the blah blah machine that at the end predict. It's very easy to train because we just have all the word, we mask, the last word, and we try to see, can you from this word, predict the next one? Well, this is useful, but it's good for generating text. Well, then we would like to talk to we would like to have a conversation. So we'll make it a dialogue. And so for that, we use, instruction fine-tuning. We make the model, we change weights a little bit and make them to follow instructions. And particularly one of the instructions is like, talk to me, be a dialogue with me. And the one way that we do it, the data that we use for that, we usually pay, external partners. So these are the big companies like Scale, Search, and billions of others. I have to talk to them like every week. If some of them like provide the data, some of them provide even synthetic data. But the data are the form that for this prompt, what should be the right answer, right? So like the humans will actually write some answer, or we can actually even ask, well, give me the more prompts and answers in theoretical physics. So right now we have the answers, so the prompts, the questions, and the answers, and we also we want to make sure that there is kind of the turn taking. I speak, the large language model speaks, and so on. Well, then comes a phase that I work most of the time, which is alignment, because as this, all these large language models I train on all internet. And internet is not the nicest place. Like the conversation you had in Reddit, Twitter, 4chan. These are not the most nicest conversation you could be having. So you would like to make sure that the models that we release are kind of aligned to preferences we would like to have. Aligned to some kind of human preferences. And so, for example, you would want a model that's nice to us, that follows instruction, of course, improves the capabilities, but is also not sexist, not racist, not a financial advisor, not a doctor, and so on, right? And all these things, it doesn't have some kind of try to minimize possible biases that it would have. And so for this phase, it's what's called reinforcement learning with human feedback, or alignment, or so there are different words for that. And the way how it goes is that we take a model and we try to find like a checkpoint. We call it checkpoint. It's a set of weights of a neural network of transformers, and we try to find another checkpoint that you humans would prefer to this one. And the way that we do that, we, for example, take the checkpoint that comes here at the disease phase, and then we generate 2 or 10 different answers for some prompts. Like, let's say we take 10,000 prompts, we generate 2 answers for each of the prompt, from the same model, and then we ask humans which one of the 2 would you prefer. And then then we have this checkpoint, and then this is something that if we're happy with, we release to the humankind, or it depends what your business is. You can sell it to companies, you can sell the tokens, and so on. Yes, please, yes, thank you. Yeah.
I'm curious, when you add reinforcement learning, in this pipeline, how do reward functions look like? Because at this point, I can't imagine, because I know how the language models are trained.
Yeah.
When you add reinforcement learning, reward functions, how they look like?
This is the rest of my talk.
Okay.
Yeah. So that is all that my talk is about the reward function and how to actually do it better. Yeah, but that's a great question. But before we need to do a little reality check with what actually we could achieve with reward function. So if you remember let's say big discoveries of deep reinforcement learning, mostly down in DeepMind, like the games like Atari and Go. We took relatively small networks, number of parameters I'm not allowed to say, but it's very, very small compared to what we have now. And we train it to 10 to the 10 training step. And at the end we had, little Mario brother that, you could jump and, eat some mushrooms and so on, right? And so now it's completely, reverse. We have the models that are more than, more than 400 billion parameters, and we do sometimes not even 1,000 steps. Sometimes we do even a few hundred steps of reinforcement learning. So we cannot really expect that we will have completely new, generative behavior. So we need to take as much as possible. We have to squeeze as much possible from this small number of steps for that many parameters, right? So we cannot also expect miracles there. And so we need to actually make sure that what we are asking is already well pre-trained. We start from some set of parameters are already good, and we can refine them, right? It's very unlikely that we will discover completely new ways of conversation and completely new ways of alignment, right? And so we have this kind of the phase that's being used, let's say in GPT-3 and 4, and Llama 1, 2, and Gemini 1. And the rest of the talk, I'll tell you, this is not a good way to do it. And I'll particularly focus on the last part. And so this is slightly more in detail what we are doing. And so maybe just a small summary, what I'm going to talk for the rest of the time. So as I said, let's say in the GPT-4, what we had this kind of pre-training, supervised fine-tuning, and we find one checkpoint that humans would prefer to this checkpoint, right? Like if you do the game theory, this is called best response. You want to find one set of parameters that this policy, that this agent, that this whatever it comes up with, humans would prefer to this one. And then they say, well, it's better than this one. It's best possible response to this one. The humans would prefer it best, among all the humans we prefer best. And so I think, well, this is actually quite bad. It's weak. What if this is already bad? I came up to my training point some in an arbitrary way, and I just found one checkpoint that's better. So what I'm arguing for right now, a main thing that I would like to achieve here, is to convince you that this is not enough. I would like to have not one checkpoint that's better than some arbitrary one. I would like to have one checkpoint, one set of weights, one transformer, one language model that's better than all other checkpoints possible, right? I want my Llama 3 and Gemini 2 be better than, my pre-training step, of course, but also with Llama 1 and like all possible weights possible, right? So, I ask for much higher, my goal is much higher because of course I want to be better at this one, but I want to be better than everything else. And so for now, I'll try to convince you that this is a good strategy to have. And so for that, one thing that we'll do is just we'll train the different models, to kind of generalize from human preferences. So right now, what we are doing, like let's say in GPT-3, is that let's see, this should work even pointing at the computer. Oh yes, it does work. And so what we do, we pay millions to people to do the to label which of the two responses to have, right? So we have one prompt and two possibilities, and humans say I prefer this one to this one, and so. And what we do, we kind of train it to predict ELO score. So ELO score is something that we can use in chess or something like like in ATP ranking in tennis. And this is a familiar score. They're called Bradley-Terry model or BT model. And so we would like to have humans do all the preference and all the data, but that's very expensive. So instead of we use the data we have and we train the model that kind of imitates the humans. So we take the prompt X and the answer Y and the completion Y, and we train the model that predict the ELO score. So we say like for this X and this answer, this is the ELO score. So this is the objective function to do it. Bradley-Terry model is very, very simple. It's 6 sigmoid of the reward of ELO score of the winner, the one that humans prefer, minus ELO score of the user. And then we just train the model to prefer. So now we can try to see like why my method is called gamification, because you have kind of two competing things. You have one answer where there's another one, and you would like to, you have two answers, y and y prime, that compete each other, and you would like to find one that has the highest ELO score. Right? So like that, right? You would like to have the best. And and so for the stuff that I'm trying to do, I'll try to train a different model. So I will not be preferring ELO score, but I'll be preferring the preference model. It's almost the same. Same network, same number of parameters, same data sets. I'll just train it slightly differently. So instead of training ELO score, I'll be training the X, my prompt, my answer, my alternative answer, and I'll try to train the model that would predict how much average human would prefer y to y prime. And I also train it with supervised learning. So instead of going ELO score, I'll try to preference score. Same number of parameters, same number of training steps. So no change that we need to do in our framework, which is very important because we invested quite a lot to have this model. And the reason why we actually do that instead of asking humans all the time, because first it's faster and it's much cheaper, right? So once you have humans that generate this data, then you can train a model, and then you don't need to ask humans anymore. And instead of whenever you would like to compare anything, even the things you have not seen, you will be able to ask your models itself. All right. So now I'll try to first, argue that these are kind of two different things. And so, Bradley-Terry model, it's it's assumption, it's a model, and I'm telling you it's not a good one. And so don't get me wrong, assumptions in science are good, right? This helps us advance. We extrapolate a lot of, things that we don't care about, or we reduce number of parameters, so we can, we can have a simplified model. But here, and we get something from it, right? But here I'm kind of claiming we don't get anything from this assumption, right? We have same number of parameters. So why would we, in addition, assume something that just potentially hurts us, right? What if my human preferences are not following this particular sigmoid, right? So I'll try just to not assume anything, or almost anything, right? I'll assume that, the preferences of humans are just anti-symmetric. If I compare the ones versus the, flip ones, it's just y minus the other. And so then I can define the preferences of one completion, one output of the ChatGPT towards output of Llama, to be on expectation, random human set taken from the population U, and this is function that human Z, that could be deterministic, some scoring function, I don't know what it is. It's that on prom X and Y, this is how much this identity function that for that particular prompt and completion, humans have preferences, and they have expectations over the all populations of humans. Well, then just by this definition, I just didn't do anything, just define things. That allows me to train probability winning from the model. So this was the definition of how one completion is preferred to the other one. And so I can generalize to how humans would prefer one model, let's say, Llama 3 to, GPT-3. And so the definition is that, if I take, some completion with one model and another completion with other model, then, it's on expectation how the humans would prefer it, to this one. So this is what we call probability of winning. So once I have probability of winning, I can just very simple define what I wanted. I want one checkpoint at the end that humans would prefer to any other checkpoint. This is very simple, Nash equilibrium from 60s, right? I would like to find one final large language models that if I compare to any other model, it will be preferred. Potentially this may not exist, but this is what I would like to. I would like to have this argmix max-min function that the humans would prefer, and just the definition of preference allows me that. And so first I would like to convince you that I did this little maybe a little just rewriting of things, and this could be almost the same. So it'll be useless that I talked about. So this is just a simple example that probability of winning versus best response are not the same thing. And so here I took some random prompt, what's the capital of Slovakia, and three possible answers, and I just compared how humans prefer the answer, right? So there is 1/2 on the diagonal because that's the same answer. So normally we prefer same things with 50%, and I made it so that this actually follows Bradley-Terry model. So even if actually your data follows the model, which in general doesn't need to be true, in this case it does. Right, and so the Bradley-Terry model is followed that, you have reward of first answer is 0, second log 9 and log 2, and, and the preference is then it's sigmoid winner minus loser. And so, and in this particular case, actually, if I, optimize for maximum reward, well, very easy, right? Maximum reward, it's, I'm very bad in pointing, maximum reward is log 9, right? So it's deterministically choose random 9. Maybe I should mention that when I'm predicting with large language model, it's not always a deterministic answer, right? So every time I ask large language model a question, we have a different answer, and this is because, this is generated autoregressively. So first time I have a world, or what we call token, it has a forward pass of transformer, it generates a set of probabilities. I sample from these probabilities, and then I get the answer. Then I put my token at the, next to the first one, and I sample from the answer, right? So my answer could be deterministic, so in this case 0, 1, 1, or it could be stochastic. So I could have different kinds of answers. And so here I'm showing that, like, well, if I optimize for maximum preference and best versus maximum reward, I get the same answer. And then you could say, well, you know, why did you waste our time? Well, the thing is that usually in the reality, we do not optimize, we don't use unconstrained optimization. The thing is, because if we would just like blindly optimize for maximum reward or maximum preference, the data that, so the models that we use to generalize human preferences, you know, are only good with some vicinity of those answers, right? If we ask, if we just maximize blindly this thing, you know, it's very easy to get very high numbers, but you know, the model is not very good when what we ask is very far. So that's why if you blindly ask it, we get with the model that outputs pizza, 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 because this is like what model likes the best. Or for example, smileys. You know, we train these reward models and we put in smileys independent of what is the input. This is the best reward. So that's why we cannot go really far from the data, and that's why we constrain our optimization, not go very far from the data. So let's say in this trivial example, let's emulate not going from to the data. We just put the constraint that probability distribution, you know, for the second, it will be such that, you know, probability of second is twice the first one, or not the other way. And so this is just a very simple example to show that once you have it constrained, as you have in the reality, you get this different answer. I haven't convinced you why it's better. Here I was just to convince you that these are different. And you know, like if you actually want to do the computation yourself, right? You know, it's pretty simple. Like, so if you maximize the reward, so you want to have a best reward. So like this is this kind of mixed answer that will have, you know, some number bigger than log 2. But if you take, you know, the stuff one was in, the previous slide, you know, this model with the p, you know, pi p, it will be, you know, 5 over 99, which is bigger than 1/2. This is just to say these are different. Right? The main point is that I'm trying to make. I'll provide you 4 arguments that not only that's different, but like the stuff that I'm arguing, it's better. I'll try to convince you, right? Because it's I think it's more important, like how to get to how to compute it, is to actually convince you that what we are computing, you know, your question is the right one. So I'll try to give some intuition rather than like, going over definition. So imagine, well, we just had an election in the United States, right? And you have data, well, let's say they are biased or opinionated, and you have half Republicans and half Democrats. And let's say you have just one data point that's Republican. Then if you go for best reward, then your large language model will be all Republican. Because, the best, Bradley Terry, or as we say here, winner takes it all, right? Win the election, you can do everything. So what we have that just one majority takes overall everything. And it's actually quite fragile, because if you have 2 more data points that are Democrats, everything, the policy, the large steps, and everything is Democratic. And this is because best reward, Bradley Terry, optimizes. And this doesn't need to be even absolute majority. You can have 100 different, let's say, subgroups of people, and one is just relatively bigger than the other ones. Then winner takes it all. It takes over of these preferences of the, relative, majority of the people. While if you go for Nash equilibrium, you get a mixed answer. So let's say you have roughly half Democrat, half Republican, then your output would be such that half of the time you get Republican answer, and half of the time would be Republican, or the Democrat. So, this is kind of catering to like the diversity of population better. It's the first argument. You may not want that, right? Maybe you're a corporation that wants to have one opinion, and maybe that you don't want that, right? That's a question I was asking Google actually. The other thing is coming from that, why assuming some model gets you something that it may be not true in reality, right? For example, in chess, right? We can do the ranking, so every chess player has a ranking, so you already know which one is better because you just compare the number. But let's say you have a circle, right? So, in tennis, I'm better than Chermo is better than Vinko, Vinko is better than me, right? There is no numbers that would reflect such thing, right? If there are circles. And so this is a simple example. From 70, you can have like this kind of non-transitive dice. You put like one die that's 2, 4, 7 uniformly, and if you compare on expectation which of the dice gets the higher number, you have a circle, right? So the thing is that the human preferences are actually quite transitive. If I prefer something to something and something else to something else, I usually have the preferences. So this data assumption of just non-transitivity would not be bad. But Bradley-Terry assumes a lot of other things. It's a simple model, right? For example, it's non-additive. It actually even dictates how much I prefer second to third one. And this is definitely not. So this was recently discovered in a paper from Mila in Canada. The paper says like, the real games are transitive but not additive, which is another assumption. It's just very simple, extra assumption that don't buy you anything are useless to use. The other thing is sensitivity to the sampling distribution. So, how to, okay, I'll not go like defining this, but I'll give you another intuition. So let's say I am the worst chess player in Slovakia, and Rado Harman is the second worst chess player. Because I know it's not true, but so he only plays with me because that's why he wins. And the ELO score is defined in a way that like more time you play, your ELO score gets higher. And so since he only plays with me and he doesn't want to reduce his ELO score, he only plays with me and it's the highest possible ELO score. And then he looks like as the best chess player here. And he'll be invited to play with Kasparov. No, I don't have time, because if he would play with Kasparov, he would reduce his chess score. Right, so this is like kind of typical situation, right? Like, you're born in a small village, you're best there, then you go to the capital, you're not best anymore, and you face reality. So the thing is that ELO score are very sensitive to sampling distribution, and so this is even like you play multiple people multiple times. So in reality this would never happen, right? Like if you're a good chess scorer and you want to like show off, people will make you play with a grandmaster to see if you're really good. But how we actually collect data here in large language models, there are infinitely many prompts for each prompt we have infinitely many answers. And what we do, for some prompts we take 2, maybe 10 maximum, and we compare them once. And so sampling distribution, really depends on how we collect the data. So it could be completely off. So if you have like some different prompts that you never compare to each other, they could be completely miscalibrated. And so the whole problem is that, let's say I place the chess with Rado, it influences the ranking of everybody else, which is not what should be, right? If I place chess with Rado, it should only kind of influence kind of the confidence interval, how good are, like just this one estimate should get better, and everything else should be untouched because it's not related. And so this is what I'm kind of trying to achieve with my preference model. So that's why, I input, 2 possible players, so Y and Y prime, and I try to learn the preferences. And so this is, this sensitivity to distribution, it's kind of important thing. But so most of mathematical museums didn't convince the executives in DeepMind and Google because they don't really care. And but what convinced me was kind of this argument. So it just fits better, So here we had like the simplest machine learning 101 experiment. You take your preference data, 70% you train your model. So either you train reward model or your preference model, and then you try to predict how it does in the 30%. And my preference model get a couple % better. It's kind of obvious, right? Like you collect data as 0 1s, preferences between 2. You should learn something that predicts something, not some kind of nonlinear function of it. And this, this conveys direction to actually use this algorithm, use this, this is not algorithm, sorry, use this objective function and go for Nash equilibrium rather than best preference. And I have 21 minutes to show you how to solve it. All right, so this is a story about the games like poker, the trees, Monte Carlo research, and self-improvement. And so how we get to that point? So imagine the games like poker, and one typical thing of poker is that you don't see the opponent's card. So we call these, in game theory, we call it game with imperfect information. And here, like you also have imperfect information in the, like RLHF models because you also don't know all the preferences. So that was kind of the open problem, how to actually do it, somehow open problem, because we actually had optimal algorithm to solve both for perfect or imperfect information games, and they are executed practically by solving, by creating the trees, right? Like, like AlphaGo, Mu0, you create the trees, and trees are, like in chess, like I play this, he plays this, she plays that, and at the end, this is the reward. And so I kind of create the trees, and algorithms are kind of smart on how they traverse the tree and find the best strategy. The problem of this, that while this is good enough for Go, chess, game with perfect information, with imperfect information, number of nodes of this tree, or we sometimes call them information nodes because we don't even know what the old states are, what all cards are, can be really big. So this is one example of a game called Stratego. The number of states is 10 to the 1,000. And so we cannot have trees in memory that have that number of states. In deep reinforcement learning, so which was used for solve Atari and Go, there is one kind of practical thing that we still use after maybe last 20 years. It's called replay buffer. So the way how we actually distribute computation to solve this huge problem that we have, some kind of current policy, our current best playing algorithm, and it plays, you place the two players, like let's say Go or chess or poker, right? And so these are, you need to play fast, and so you have TPUs. You take 10,000, 100,000 TPUs in DeepMind or like GPUs in Meta, and you make, you generate trajectory of plays, and you place, this trajectory of how, I play, she plays, I play, she plays, and this is the reward. You put these trajectories in replay buffer, right? These TPUs are very good in generating. You have small number risk architecture that is very good in small number operation, in particular multiplying matrices. And so you generate this on the replay buffer, and so you have a replay buffer, and then here you have one CPU, simple CPU, that takes some trajectories from the replay buffer, 16 or 1,000 trajectories, improves the policies, and then distributes this new policy to these 10,000 of TPUs. And so this is the way how we actually manage to scale, many algorithms in reinforcement learning and deep learning to make them and to have these discoveries, let's say. The thing is that for the game theory, for like the big or imperfect information games, these algorithms that we had with replay buffer are not optimal. And so the open problem was like how to actually have an algorithm that gets us to optimal solution and is not able to construct the tree. With the tree, we know how to do it, and how to do it without tree, that was an open problem. And so, so to actually make that possible, we needed to have like a good loss estimate, because we don't know the true loss, right? Some regularizer, balancing, and some kind of secret sauce, that put all together. And so this is something, that I spent last 10 years of working at. At the beginning, it started with a very simple, it's called the bandit problem, like multi-round bandits and casinos. How to have optimal algorithm that would not have explicit exploration, so it will be only implicitly explores. And so I created something called implicit exploration. Now it's part of some modules, 10 years ago. And from that, it took 10 years actually to find the final solution to this open problem. And so if I summarize my contribution for science is whenever I saw the fraction, for example, here in implicit exploration, Implicit distribution practically is done that you take the loss over the probability of iteration and you add small gamma t. So if I summarize my contribution, it's like whenever I saw a fraction, I added plus gamma to the stuff, right? So like many of the discoveries that I had, 2008, graph cuts, the lyric K-score, spectral bandits are actually of that kind. Whenever I see the fraction, I guess plus gamma. This is if I'll be ever epitaph, Michal Valko died somewhere, when it's a fraction, yes, well. So the contribution could be kind of practically very small. And so this is one of them, and so there were other people that tried to, that they were improving on top of that, right? So the Crover for NYC created something called dilated entropy. Actually, how do you compare the trajectories? Gergely, my postdoc, was doing like high probability bounds. Monte Carlo, CFR, was a guy at DeepMind doing. And so there are many, many other people that try. Then Shijin from Princeton discovered that you could do. I'm very bad at that. Discovered that you can use this implicit exploration for game theory, but didn't have algorithms. And when we get almost to the real algorithm, to the optimal algorithm in 2021, but it was kind of square root of number of states away in the speed. In the complexity, which if this is even square root of 10 to the 10,000 is quite a big number. And so we announced the algorithm because it was like the best possible, but it was still not good enough, to solve those games. So we got back to work, and since there's other people trying to solve it. So other people find that if you just look at the tree once, then you have optimal algorithm. And looking at the tree once was actually doing something simple. Like, so you need to have your policy that we know how to calculate, and then you had to regularize it with other policy. Another policy is very simple, like play with probability. So it's a tree, and you play with probability number of the nodes under the whole tree. So it's kind of like a simple thing. But to calculate it, you at least had to traverse all the tree. The whole problem is if we want to have a practical algorithm, we cannot traverse all the tree even once. And so the way how we actually solve it was like, as in implicit exploration, we're trying to merely explore. Here we will pretend that we are merely traversing the tree. In the way we actually look at what adversary is doing, and we are trying to kind of estimate this balanced distribution, one divided by probability of number of trees. Right, well, I can tell you the details over the coffee break. And so this way, we went to this optimal algorithm, and finally, we announced the result, and then we got the best paper world in ICML in 2023. And then we realized that the algorithm that we use is exactly the same algorithm that we could use for solving Nash equilibrium in large language models. And since that time of discovering this algorithm, we got to work, and we said like how we actually apply this discovery that you don't need to create trees, and you can just use the replay buffer, which is how the modern algorithms work, including large language models, right? Large language models also work with replay buffer. You have TPUs that have prompts and do the forward passes to generate completions. So on this X generate this one. So transformers, very expensive. Transformers, very expensive neural network structure. And then you have CPUs. They take some trajectories and answers from the replay buffer, make the policy better, and then transfer the policy. So this distributed infrastructure and NVIDIA stock going high, it's because of this is the way how we manage to scale the computation to 2024 performance. So this is in the rest of the talk I'll try to say, well, how actually we made it practical. I have both online and offline one, but I think in 30 minutes I'll just go to the online version of the talk. So it's actually very simple, right? In the first step, you create this preference model, the stuff that we discussed. So I collected data from humans, X, one answer and a second answer, and I'll just try to generalize it. Super simple, right? I just trying to learn the function, so I don't need to pay humans anymore. And the second, I'll solve it for Nash equilibrium. So practically, we will be mixing some different policies and improving the policy. But let's go directly to math. So in case you didn't know how GPT-3 is trained, in the last phase of alignment. It's actually very simple. All algorithms are extremely simple because they need to scale to these like 100,000, chips. So this is always very, 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 very simple. And so it's always some kind of gradient descent because this is what we can pass and improve the parameters. All right, and so algorithms that are used RLHF in GPT 3 and 4, they're called like PPO or DPO, and it's a very simple algorithm. So this is it's a gradient descent, but the policy, we call it policy because we also have always, every word is a probability distribution over all possible, 10,000 tokens or something like that. And so we take the grad log pi, so this is like probability you generate the word A given what came before. This is the reward. Reward, this is what comes from reward model. So the ELO score minus V, it's like variance reduction. This is practical thing. Deep networks are really bad when the reward varies. And so one of the simple things, we reduce the variance. So we train the model that learns kind of expectation of the other variable, and we subtract it. It's as simple that, and so it makes things smaller, and smaller things have smaller variance. It's that simple, and then we can, that behaves better. While expectation of those things are same because our expectation of this variance reduction thing is 0. So this actually, and so what we are going to do, we are going to, just instead of this optimization criteria, we'll go for this one, finding the Nash equilibrium. This was actually very unexpected behavior. So that was practically useful. So for this, here was yes. To find this variance, it needs to be a network that's usually the same number of parameters as reward model. So this is just to reduce the variance. We need to have, for example, largest lambda 3, 405 billion parameter network that just outputs one number that should be expectation of the numbers of other network. It's kind of wasteful. But what we find in an unexpected benefit that equivalent of variance reduction in the let's say RLHF in GPT-3 is to reduce the variance by comparing the Y to Y itself. So given the prompt, you want to compare how much you prefer Y to Y, which is trivial, which is 1/2. So instead of training, and spending, millions or tens of millions to train, 4 or 5 billion parameter network, we just replace it with 0.5 in the code. And we did that much of saving for each experiments we run. So we have this variance reduction for free. The one thing that we are not solving in a way with this approach, but we still need to address it, is reward hacking, right? So when we train this reward model to tell you on this prompt, this answer has this ELO score, and if you just maximize, which answer will have a higher score, right? This is we get pizza, 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 because that has, independent of prompt, pizza, pizza, pizza has always largest score. So the way to counter that, he said, well, you cannot do pizza, pizza, pizza. In particular, you cannot change your parameters too much. So you start with supervised fine-tuning, so that were probabilities are such, so the weights were such. So you cannot go very fast. So this is the a KL divergence between the. So you say, well, maximize the reward, but don't go very far. So maximize minus KL divergence of the previous network and this one. So now you would like to do something like this. So what we could do, we said, well, maximize, find the Nash equilibrium, but don't change parameter too much, some kind of constrained Nash equilibrium. So we could have done that, but we did this some hack instead, which also turned out to be quite a good hack. And the way that we do it, so if we compare, let's say, two different chatbots, two different LLMs, you have probability one bigger than the other one. When you say, well, this is the number that comes, but if either of them went too far from the data, then reduce proportionally bical. So for example, if you have a new chatbot that's better than this one, but this one is kind of very far, then don't trust this as much. So this is minus reduce reward. And the other way, symmetrically, if you're better, that's something very bad, well, I don't care that much anymore. So we thought this was a hack to solve reward hacking, but I actually found out that it was very useful because this adds additional convexity to the problem, such that this regularized Nash equilibrium, because you can see this minus KL and plus KL, is unique. And once things are unique, so you can just much easier find it. You get fast conversion redistribution and you get the last iterate conversion. Last iterate conversion means that as you're improving your large language model, the last policy is good. While most of the game theory results that you keep improving, and the result we have is that we need to sum all these models, some of the outputs of these models, and we have guarantees on that, which in large volume model is quite bad. So the other thing what we could actually do, like why are we inventing new algorithms? Because Nash already solved it. Why we have to do something in 2024 if we could use Nash algorithm from 1960s. So this is the Nash algorithm from 1960s. You start with the base policy. So here, supervised fine-tuning after the second step. And you find one policy that's better than this one. It's called best response. This is actually what ChatGPT does. Actually, the ChatGPT is like the first step of Nash algorithm. But you don't stop there. You take base policy and improved policy, two of them, and you find one that's better than the two. Better than all possible mixture of the two. And you find better policy. Then you take three together and find something that's better than this three one. This is called solution concept. Yeah. And then you have a guarantees on this one. And you go until convergence, and then is a Nash, which is the best overall. And there's no problem that we didn't prove that Nash was wrong. The problem is that every of these policy is a 405 billion parameter network. And you cannot store every time step 400 parameter network, and every time you want to generate the new output from this 405 parameter network, we just average them all. It will be really expensive. So that's why we had to do something else. And the stuff that we had, from our, paper work in 2023 is some kind of very, also very simple algorithm, mirror descending. Mirror descending is also something we didn't invent, It's coming from Nemirovsky, a few decades ago. The algorithm is also very simple. So you want to find, Nash equilibrium for this probability, for this preference distribution. And so the way you solve it, that every time step, you improve the policy. So this is called policy improvement step. So it's the best response. This is some kind of regularization parameter. So you improve the policy in every step such that you don't go very far in each step. So this is between pi and pi t. So you don't go very far in every step. You improve it, but you don't change things. So it's kind of conservative in how much you improve. And we have a guarantees for that, even for large language models. So this would be also very, very computationally ineffective to implement, because what you have to do, you would, every step you would need to solve this maximization problem. So it's every time step you would have to do something, let's say that ChatGPT is doing once. So very expensive. Instead, and this is a jump from theory to practice, no more guarantees. You say well, how do we implement don't go very far? We say, well, if you just do one gradient step, you don't go very far. Believe me. And so instead of this, we just actually don't implement it. Instead of Rmax, we just do one step of that function, of this function, and this will just say, well, we just do one step, hoping with one step you cannot go very far. The other thing that we do is that so then just means that you just need to take gradient of this, right? The gradient of the p, preference of one bigger than the other one, minus minus the KL between the policy, between the one that you're trying to improve and the original one. And this one doesn't, you're not learning those parameters, so this is 0. And so actually the KL that you get, KL divergent between the two, is only just the first one. So what is actually very beautiful about here is that this is almost the same as the original, let's say, ChatGPT. So we actually don't need to, change much in algorithm, and because our software, our algorithms are optimized for that. And so here we replace huge network with 1/2, if you remember. Here we replace, compared to ChatGPT, reward model with this preference model, and here it stays the same. So the gradient descent we do every time step, it's kind of the same. The main things that change is that in ChatGPT, for the results, you always had, you take the current version, you generate 2 answers for the same prompt, and you try to see if, with reward model which one is better, or you just generate just one and you get a score and try to maximize the score. Here, because it's a game theory approach, we actually generate things from 2 different policies. So one is the mixture. You can think of it kind of, this Nash mixture was trying to mix the policy. And one is the current policy. So we have a current online policy, and we have this mixture policy we want to improve. So this is how we get y and y prime that we improve. So practically, so we know exactly what we were doing. At the beginning, you have your supervised fine-tune policy. Step 2, you just you have your prompts, answers, and you want to make it aligned to the human. You take the policy, you define one that's better than this one. By 1 gradient, a little better than this one. What you have, so you have a better policy, you take it, you take 75% of this one, you mix some old one, so you mix the weights, you meet 75% of the policy of new one, 25% of original one, you have a mixture policy, and then you improve this mixture policy. Delete the other one. New policy, mix 25% of old policy, improve. Mix 25% policy, no, improve. And mixture is it needs to be geometric mixture, for the theory to work. But it's actually very easy because what we are predicting in the end of the transformer logits are not the actually mixture. So geometric mixture of the the original policy, and the new policy, it's when you take the log of this, because that's how it's represented in neural networks. It's just like the basic arithmetic mixture. It's just average. It's just weighted average of 2 things. So practically how it works, how you generate, because you don't have this mixture policy, you don't need to have it. So you take one network, another network. You take the first token, like first word, you do forward pass of this algorithm, you get your probabilities, you mix them arithmetically, then you generate first word. You take the first word, get it to the both network, do the forward pass, second word. Do the forward pass, third word, mixture, fourth word, and so on. And then you have a thing from the mixture policy. So this is the algorithm, that's at the end, 1 line in the code. And so obviously what is important are the results. And here I spend little time because we have a different objective function. So we will go for something else. I have 1 minute, so I'll only describe the results, and this will be it. So this is your supervised fine-tuning policy that you start with. And these are all possible algorithms you could have, and their final networks, right? So this is RLHF, ChatGPT, this is self-play, this is our algorithms with different mixtures, and this is best response, and this is some other algorithms, right? And on the column you have exactly the same algorithms. And you try to ask humans which one you prefer, because that's what matters, right? We want to have one algorithm that's preferred to all. So if you prefer one chatbot to other ones, you get 0.5 always, because they give you same answers on the diagonal. And so first, what's the original thing? You start with SFT, and the original thing you would do RLHF. So RLHF gives you, after you do like ChatGPT optimization, humans would prefer the new version 99% of the original one. And with our approach, it's actually less. So because the RLHF is indeed the best response to the reference basic policy. So we did something worse. So maybe we're bad. The thing is that, if you compare the output of RLHF, well, compared to one policy, it's better, but compared to other policies, sometimes it's a little better, sometimes it's a little worse, sometimes it's better, sometimes it's worse, right? So, it's better, it's the best possible response to one, but, to the other, we never cared. So sometimes it's better, sometimes it's good. It's like, 50 plus, 50 minus something. While if you look at our column, our policy, it's slightly worse best response to SFT, but if you compare to everything else, is always better. Well, naturally, we optimize it this way. And so this, this result was actually convincing enough that this was included in Gemini 2, in the current version of Gemini 2 that you communicate with, and in Llama 3 and the products. So I had also offline version of this algorithm, which behaves even better for practitioner in the case, but I already exceeded my time, so I'll just say thank you very much. And